Okay, so I'll just get right into it. So I'm starting with this thing about what am I like presenting, how and why. So my thesis, which I consider as the destination of this research, is really thinking about total array languages for handling heterogeneous GPUs. So if you think about, or if you know about scheduling languages, you could think that I'm kind of like trying to embed a scheduling language within this total array language. But then this talk is really about getting towards that destination. So it's more about crossing this I/O boundary to the total Lean 4 world in which this language is implemented in. And then the kind of like main topic today is regarding this fold which parses but also computes your type. The way that I'm going to do this is by presenting this graded monoid over two folds. The one is a partial thing, so it's a monoid accumulation which transforms something like when you read a CSV which you have values in it, then it tries to map those into integers. So if you have something like even in Lean 4, if you have 0, 7, and then you have 7, those both map into the same integer, even though the string is different. And then there's this total or more like shapely type kind of part to it, which is that, well, if you just have the length of your list, then that's isomorphic to producing a vector of the same type in which the n is kind of like attached as an existential. And kind of like, why am I even approaching this problem this way? Well, in this language I'm dealing with, everything is a fold. So these recursion morphisms become a central concept, and then I'm going to show you two particular ones, katamorphisms and zygomorphisms, and how those interplay with the parsing. So the one thing about this approach is that you can just pick any monoid you want, and you should pick one, which kind of like represents the properties that you find interesting in your data. So in the submission, I chose this cast monoid, but kind of like anything which can just do this ornamentation or production of length to your data will suffice. So as long as it kind of like carries this accepted field. But then two other things that I kind of like wanted to, or I showed in the paper, was regarding these steps and rejected part, which are then two different things that happen during the parsing stage. So you could think about steps as this rudimentary optimization thing. If you would have two different programs or kind of like solutions which produce you the same result, when you index your fold, and I mean, in this language, everything is a fold, so you can just index the whole program, then the steps can be as a way to kind of like see that how does this like a program composition accumulate operations within it. Then the rejected one can be seen as a complement type. It doesn't necessarily have to be like strictly complement, but here I'm kind of like collecting that, if something wasn't accepted, then at what location did that happen? And maybe you could also have like, why did that rejection happen? So as an example, let's consider this matrix of CSVs. So you can just strip out the columns and kind of like this T1 and S1 thing. But now we are running this katamorphic graded monoid. So if we flatten that input string, and then our partial parsing step is just a two-integer function, then what this produces us over this katamorphism is this type, which is a sigma thing, with the first element being the cost A monoid that we just saw, and then we have this vector A C dot accepted, in which the that's the output data, and then the length of that data comes from the monoid accumulation. So as we can see that, yeah, we accepted 5 elements, which are the 5, 3, 9, 1, and 2. We did that in 14 steps, and then we rejected 9 blanks. Relevant next questions is that how do we kind of like, what's the structure here regarding these indexing monoids? And then also what of this information actually survives to the total post-processing part? So the correctness kind of like assumes this thing that, well, you should definitely be able to run the index algebra, the cost A, on its own without kind of like having the vector part there. So this is also seen as a monoid homomorphism. So from the square, you can kind of like see that if you have a base functor f, in our case, it's just list, and then you have some scheme like a katamorphism, you can take the projection or the first part of the graded monoid, which is the pair, to get from fa to f pi, and from there you can get to the cost thing, and then land on the grade of your computation. But you should definitely also be able to land to the same exact thing if you run both of those things at the same time. And this kind of like gives you some idea and the structure of what is kind of like what the fault looks like. It's always going to happen within kind of like this tuple pair, but you can also just run the monoid part independently of producing the vector part out. So maybe another way to think about this is through the shapely types thing. And what are shapely operations? Well, this is the, if you are familiar with the Fish programming language, that defined these, or the preceding papers defined shapely operations as something in which the output shape only depends on the input shape. So in this, all these kind of like transposes and reverses are shapely operations. But here we are treating fold almost as a one pattern which taxonomizes operations. And then we are not in the shapely world because, well, IO parsing is essentially filtering. So we are not shapely in the sense that the shape is always specification dependent, whether that's all the integers you want or something else from your IO. And then later on, I will show these 3 other ways that you can kind of like in which we have the modes for outputs regarding what we will actually see in Lean. So this is the first one is just the existential output. But then now I'm showing this another refinement of a recursion scheme called psychomorphism. So the previous example was just katamorphism view over a flat array. So there, the n in the vector an is always existential, and the output type, as seen by Lean, is something like vector a input grade accepted. It kind of like gets that's kind of like what you see in the Lean LSP. But then there's this kind of like a weird middle ground, which is a psychomorphism, and that's only about how you run the fold in itself. It turns out that it's kind of like regularity checking. This is an extension of katamorphism with an auxiliary fold operation, which essentially it peaks the first row and it looks at the structure of the first set of data that it sees. And in this case, it will see that, oh, well, there's 4 columns, and that kind of like a peak or this auxiliary fold that it saw becomes the condition for the later rows that it passes. And in this case, there is a malformed row in your input. So the psychomorphism view basically becomes this row-based parser in which these incorrectly or these racked parts of your input will become the rejected field. And then you will basically have this new existential, which is the column number in addition to the kind of like the how many rows did you have. But if you generalize this to this hypertype, now the problem really is that, well, you have two existentials, you have some regularity imposed by this more rich recursion morphism, but you cannot really even do like any kind of equality proofs in Lean about the interdependence between the existentials that the psychomorphism just produced you. But this is kind of like a way to have an intermission in the sense that when everything is a fold, even the parsing becomes this two-axis decision regarding what is our monoid instantiation for our index algebra, but also what is the recursion scheme that we are kind of like running the parser over, whether it's a cutoff morphism or psychomorphism. There's more of these things, but this kind of like gives a little bit more refined way to kind of like think about the patterns that happen also between the IO boundary and then what comes next. And what comes next is 2 slides regarding refinements and generalization. So, of course, you can do this runtime check, and then also comp time. Comp time is probably a little bit more Lean specific, but this runtime check is essentially a runtime proof in which you can assert the size in a Lean such that it comes as a runtime proof. So either your output kind of like gets matched with that shape or it doesn't, but at least when you're kind of like running it through the graded monoid, you still have the information collected by the monoid with you. So if you reject it and the program kind of like doesn't continue with post-processing, now you at least can use the rejected field as a crash record about what was it in your input data that kind of like blocked you from doing post-processing. And you can also do, of course, this mix and match thing. So if you kind of like generalize your shape into kind of like this list-based thing, then now you can kind of like figure out where you want your existential to be. So, but that's probably nothing about the monoids in itself. The comp time is also interesting because it's kind of like what I'm doing here is that I'm moving the parser to elaboration time of Lean 4. So that gives us very nice interactive shapely types within Lean, because Lean gives you this proof tree of your program. And if you move the parsing and your input to the elaboration time, now as you go through your program and you're kind of like doing this, writing your program, you will see the concrete size of your input in those types. So here I'm passing some file which has 4,433 rows, and that's signified by the parse step. If we do a reduction, then we get a scalar value out. Then if we do a tuple, then we have 2 of those things. If we do a reverse, we have the same thing. And then now if we run a filter, now we can see that, oh, we just went across this shapely operation path because now we lost the nice concrete type, and now we have an existential again. So this does use the IO in the compile time. Of course, that implies that, well, your input has to be realized before you run your program. But this is kind of like nice for repls and prototyping. But I'm not quite sure how well this I would still consider this bit of a hack in the sense that it works, but probably I wouldn't feed it like a 1 terabyte sized file. Then there's an extra one, which is semirings, because if you look at the our previous proof regarding the program, or kind of like this, what is an index algebra? It mentioned this F part, and that's an F algebra which is type polymorphic. So nothing stops you from deriving the length from a tree. So we can replace the monoid with a free semi-ring instantiation, which is kind of nice because it generalizes parsing to recursive data structures. And if we kind of like take the psychomorphism part now, then there are these instantiations of semi-rings which can turn this into a sparse representation of your data. And again, the three modes of parsing apply here, but this is more like future work. Takeaway really fast. Parse is a type. There's one algebra. So these three different strategies, even where the graded monoid can help. This is just the data ingestion part of this lean form mechanized recursion-centric library thingy. And the next thing is what I've been looking at is these other more complex recursion morphisms like paramorphisms for modeling SIMD operations over varying subgroup lengths, how cost-optimal schedules are seemingly dynamorphisms, and how these mental algebras seem promising way to reorder recursion morphisms within different kind of schedules. And that's about it. Thanks.
Questions, if there are some? Oh, yeah.
Oh, okay.
So this one will go to the stream. This one,
Okay.
the author will actually be able to hear.
Hi, Juuso. Just to understand some of what you presented in a practical context, would this be a use case? Like if I write a sparse array where the array dimensions are a function of, are computed, and you are able to type check it using lean, or are you able to generate a lean proof script and also explain when the proof doesn't go through? Is that what I understood from the general gist of what you presented? Yeah.
Yes, so if you would have a post-processing step which you have proved for certain kinds of shapes of arrays, then you could parse your program to check whether some sort of input passes or produces you that type that you need for your proved post-processing pipelines. Then yes, you can do that.
Much for this. Ooh, sorry. So there's another idea where you can use graded monoids on numeric types to talk about things like dimensionality and units of measure. So can you do something here to kind of, and there's a way of doing this also, I think, to give units of measure to arrays where the unit of measure kind of varies across a row. So can you do something sort of similar here where the graded monoid is kind of like pushed down to the elements on the inside as well, like it's talking about the elements?
Couldn't get not properly, so maybe if you can repeat.
So I think the question at high level is like, can graded monoids be pushed down to the elements as well?
Elements as well. I mean, the...
Yeah, can you... He can't hear at all. Okay.
No worries.
Are you safe? So
Hi there.
there's this idea that you can do units of measure typing with graded monoids. So like make your like floating type be a graded monoid where it's like graded by the, well, it's something like the free abelian group to describe the units of measure. And then you can do this over an array to talk about like a varying unit of measure at each element. So can you do something similar in this framework? Have you thought about this?
No, I haven't thought about this, but sounds like something I should look into. So that's free abelian groups.
Yeah, I can send you a paper that's about it. It's by Connor McBride and Fred Forsberg.
Yes, I would certainly appreciate that if you would
Yeah.
send that over to me.
Okay,
Right?
thanks.
Cheers.
A mini panel at the end, so you can join back after one more talk. Okay?
Got it.
Yeah. All right.
Thanks.
Yeah.